Good morning, everyone. Could we have those whose mics are on? Mute it. Mute your mics. Mute your mics, please. Those whose mics are on, mute it so that we have minimal noise at our background, and we can be able to get ourselves very clear and loud. Yeah, is that okay?
Yes.
Yes, I want to have whose mics are on. Mute it. Well, I will. By Yaaka Digital Network. I am called Yandu Amos and the learning facilitator for physics. This is yet another edition of the lesson. It is the second time we're having this. I think for those who have just joined us, feel free to interact. At the moment, we're going to be asking questions and then you'll be contributing. Those who were there for the previous lesson, let us be very active like the way we did. These lessons are yet free, but for you to continue enjoying these services, you need to enroll fully on Yaaka. Yaaka provides a number of services. You can go to the next slide. Yaaka provides a number of services which range actually educational services for many of us in your category. One of the services that we provide is this online that run at 500,000 Uganda shillings per year, which is you'll be able to have teacher-student interaction by holding class engagements. Someone saying what is not getting me. Hello. I hope I'm being loud and clear. We have a lot of interactions here, including class engagements, access to courses. We have subjects of all these subjects that we have in your curriculum. They're going to be sorted out here. You'll be sorted in all of them here. We have marking and grading of your assignments. We have by the ready assignments on our site. So when you enroll fully at that price, you'll be able to enjoy those. You'll be able to do those assignments, quizzes, and this happens for the whole year. It is 500,000. Even you can go to the school and you keep on doing this as you continue to be there for what is in class or what the teachers are able to give you in the school. So you can also be able to access downloads. You can download notes, classwork, but a single one goes at 10,000. But for all the subjects in each class for primary, it is at 30,000. Meanwhile, all the subjects for the secondary class per class goes at 50,000. These are very good services that you don't need to miss. We are working in line with Educare. Educare has that website of www.educare.biz. You can also access P1 to Senior 6 quality learning notes, and these notes include a couple of videos which are very good. They make you to understand some of those so easily. So our membership levels are just been shown on that slide there. One is we have actual 2 days free access. Then Ugandan shillings 20,000 per month, where you can enjoy also 50,000 quarterly, which is in a period of 3 months. At 50,000, you enjoy those learning notes and videos. Or if you want to do it in a half a year, it is 70,000. If funds cannot permit, you just go straight for the 100,000, which is annually. So those contacts below there, you can be able to access in order to get more of this information. Now I want us to move to what basically we're supposed to be looking at today. We're going to learn about work, power, and energy. Work, power, and energy. This is a topic in the mechanics, and then we have to start it right from work. We shall look at power and energy one after the other. Start it from work. I want us to consider a box which is being pulled on a rough ground, and the figure has been shown in the next slide. So there are so many forces which are acting on that box. Can move to the next slide. We have a couple of forces acting. So we're supposed to use that figure in the next slide. I want us to study it. Next slide. That a box is being pulled on a rough ground. The figure in the next slide shows the forces acting on it and the direction of motion. Could you move to the next slide, please? So in that, well done. In that diagram, as you can see, the other time we looked at types of forces, okay? Those who are there for the previous lesson, I know many of you were there. We had so many of you who are there. Language, Bridget was one of those. We have maybe by swap of hands, who are those present for the last lesson? You can just swap your hand by swap of hands. Who are those present for the previous lesson? We have that in the names of Pearl, someone in the names of Abadi, then someone I am quite sure of Bridget, who was also there. Now, in the previous lesson, we looked at the various types of forces and those effects of forces. We have, you can see, pushed by the applied force, move in the direction of the applied force. It is because that force is very excessive and it is strong enough to move it. But you have the other force, which is the reaction force, which acts in opposite direction to the weight. The weight is actually down there. It acts towards center of the earth. It acts downwards. Meanwhile, the reaction force is the action. I mean the reaction to, as we can use that word again. Weight is the action force. The reaction force is what we have that acts in the upwards direction from the box. Meanwhile, the friction force acts in the other direction to apply the force. Now, we shall have to realize that after this, when we shall pull the box on applying that force, what happens to the box? What do you think will happen to the box as we pull it there? Those who wish to contribute, you put up your hand, then I give you the chance. What happens when you apply that force? What will happen to the body, to the box?
The box will move.
Good. It moves in that direction where the force is being applied from, isn't it? It will move in that direction where the force is being applied. Now, as this box moves, we shall say that some work is being done. So I said that some work is being done. So the work is being done in moving the box in the direction in which we have applied the what? The force. And then that now enables us to define what a force is. I mean, define what work is, because it is after we have applied some force, and then this force enables the body to move in the direction of the force. Now, based on that, who can be able to define for us what work is? Who can define for us what work is? Sharifa.
Scientifically, work is the product of force
And the distance? Hope, is that the same thing that you were going to say?
No.
So can you have this?
Like, work is the product of force and distance moved in the direction of force.
Very good. I think that was going to be the same thing she actually was going to also say. It is the product of force. Next slide. It is the product of force and the distance moved in the direction of the force. Now you can find that when now work is done, that's now what we were bringing in the next slide. We're saying work is done when a force acts on the body, and then we were able to see that from the previous slide, force acted on that body and it made it to move. And its movement was in the direction of the force, isn't it? So from there, which means we can be able to calculate our work done from what we have there as the force times what? The distance, which is moved in the direction of the force. And we usually use in this perspective, we use capital F for force and small d to represent the distance. I want Hope is back. Hope, read for us how we define work.
Work is defined as the product of force and the distance moved in the direction of force.
Very good. Work is defined as the product of force and the distance moved in the direction of the force. The force that you apply has to do the work. See, what you call work is now that distance, the product of the distance and the magnitude of the force. But the distance that is moved has to be in the direction of the force. We are saying, we are proceeding to say there that the SI unit of work is what? The SI unit of work is?
Joule.
Joule. So when you are writing, I want you to be very careful here. You might be asked to, a question might ask, state the SI unit of work. I know when you are just saying it in words to be very easy. But when it comes to examination, writing down, in physics, we mark it up to how you write it. You know, Joule, when it is written as a unit in words, you have to start it with a small j. With small j. And then when it is written as a simple, we put the capital J. I know you are able to differentiate between capital J and small j. The computer usually does some kind of, it tries to actually, I can say it misinterprets for us that, and the way it puts the capital J, it's not the way we are required to have it. So when we are writing the J, the other head that cuts across there has to be. So it is capital J when it is as a simple, but small j when you are writing it in words, we start with small j. So we have the other unit of work, which is a kilojoule. Kilojoule is written with a small k and capital J. So you have it well there. So which means that in 1 kilojoule, there are 1,000 joules. Okay?
There's banging here.
In 1 kilojoule, there are 1,000 joules. So now, someone saying, could that person put off the mic? Now, as we continue to have our lessons here, particularly this one of physics, I would suggest that as we're trying to go on here, you mute your mic. Your mic should be muted. So when I ask a question and then you're supposed to be responding, you put up your hand and I give you the chance, you unmute and respond. Are we together? Now,
Yes.
we're trying to bring a concept here that 1 Newton meter is equals to 1 joule. Someone would be wondering where the Newton meter is coming from. But I want to tell you here that the Newton meter is coming from when we multiply the unit of force and the distance. The SI unit of force is what? What's the SI unit of force? Who's there to give us an answer here? What is the SI unit of force?
Newtons.
Newton.
Good. What about distance?
Teacher, are we on the right
Meters.
slide?
It's
Yes, we're on
meters.
the right. Yes, we're on the right slide, sir. Yes, the SI unit for distance is meters. Now, that makes us to have actually the derived unit for work done as Newton meter. But we said the SI unit is joule. Now, which means 1 Newton meter is equal to 1 joule. Then we can move to the next. The coordination there is where we're supposed to be defining now joule. Joule as SI unit of work is defined as we have in that slide. Want Mark to read for us the definition of joule.
Even us want to.
Mark?
And when a force of 1 Newton moves an object, a joule is the work done when a force of 1 Newton moves an object through a force of 1 meter in the direction of force.
Through a force?
A distance of 1 meter in the direction of force.
So we shall say a joule is the work done when a force of 1 Newton moves an object through a distance of 1 meter in the direction of the force. And we have to note that Gift, could you mute? We have to note that work done is against friction. Esther, mute your camera. If Esther, mute your microphone in case you are not getting us or you have another thing, and then I cannot be able to get you. You can have whatever you wished to say typed in the chat, and then I will be able to get it and respond to. We have that if we're to calculate the work done against friction, these ones are now very important for calculations. If we're to have the work done against friction, it will be given by the frictional force, because the force now there in friction is the frictional force times the distance moved. Meanwhile, if we're to have the work done against the gravity, it will be calculated from the gravitational force times the height. And then where we're actually saying gravitational force, you remember this gravitational force is given by the mass of the body times the acceleration due to gravity. What causes bodies to actually fall towards this the earth or towards the center of the earth. When you throw a body upwards, it falls towards the center of the earth. So you find the force there is called the gravitational force. The force is due to the mass of the body and the acceleration due to gravity. That's why we're saying there it is given by mg. And the height now gives for us the distance. And we all know that for our calculations here, the value of acceleration due to gravity is 10 meters per second square. Let's move to the next slide. This now will lead us to some examples on calculations. This will now lead us to some examples on the calculations. Now we had so much emphasized that work is given by force times distance. And then we said when we are calculating, the force must be in what? In newtons, and the distance must be in the SI unit, which we said is what? Meters. So as we are going to have the calculations here, we have that the first question is a body used a constant force of 5 Newton to pull a piece of wood through a distance of 20 centimeters. Find the work done. I want us to see how this answer is being obtained as the solution is worked on in the next slide. In the next slide, we're going to get the solution for this. See, they have given for us that a body used a constant force of 5 Newton to pull a piece of wood through a distance of 200 centimeters. See, the distance is 200 centimeters and the force is 5 Newtons. We're supposed to calculate work done. We all know that work done is calculated from or is given by force times the distance. That is what we have there. Now we're saying, but the force is 5 Newton. The force is in the right unit. It is in the correct what? Unit. The unit of the SI unit of force, which is Newton. And the distance is given in centimeters. Someone will be wondering why we're dividing there by 100. So we're simply trying to convert the distance which was given in centimeters to meters so that our final answer could be in joule. Is that okay? We're trying to convert. How many centimeters are there in 1 meter? Someone will be asking. How many centimeters are there in 1 meter?
100.
Teacher, you need to check the comments.
I've noted that, sir. We have 100 centimeters in 1 meter. Is that okay? We have 100 centimeters in one. Trezor, got you covered. We have 100 centimeters, as one of you has said, in 1 meter. So now you are seeing we are there trying to convert the 200 centimeters to, 200 centimeters to meters. So what we're going to do is, as we are converting here, we see we have to reflect back. When you are converting a bigger unit to a smaller unit, what do you usually do? When you are converting a smaller unit to a bigger unit, so maybe you can reflect on that. What happens if you are converting a bigger unit to a smaller unit?
You divide.
When you are converting a bigger unit to a smaller unit, you divide. Go to trial. Another one.
You multiply.
You multiply. Very good. If you're converting a bigger unit to a smaller unit, you will multiply. For instance, maybe you're converting kilometers to meter. See, kilometer is a bigger unit and the meter is a smaller unit. You will be multiplying. Now, if there's a case you're converting a smaller unit to a bigger unit, there you'll be, as the trader said, you'll be. Now, when you look at the case between distance in centimeters and in meters, meters is a bigger unit than centimeters. So we're converting a smaller unit to a bigger unit. And there we shall have to divide. And then that is why we are dividing. As you can see from the solution there, we're dividing 200 by 100 to get the 2 meters, because we're saying in 1 meter, the 100 centimeters. Are we okay with that? Are we okay with that?
Yes.
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 Then as we shall move in the next step is actually what we call substitution. We are now substituting the force, which is 5, and the distance, which is 2. And when you multiply 5 by 2, you'll be able to get 10. And we conclude by saying that's the work done is 10 joule. One thing about calculations in physics is that if a question is asked, know that you're going to be marked 3 areas. One is you will be marked correct formula, and then the second one is the correct substitution. Substitution has to be without the units. In substitution, we do not include the unit. Substitutions where we are having now for this case is where we're having 5 times 2, that is substitution. And our answer has to be answer with unit or answer and unit. There are cases where the unit cancels out, so we will have answer without unit. So there are cases where the unit will be there. So this is a case where the unit is there, so we shall have to bring the unit at that step. Let's move to the next slide. We have another example. Let's have another example. We have another example here. Someone is trying to give us suggestion or who is talking? Gift, could you put your video off so as to save us in data? Start to save some data for us. Could you put that video off? I think it is Dennis Ruth who's talking. Ruth? So question 2 is saying a shopkeeper lifts a tin of mass 2 kilogram vertical through a distance of 1.7 meters. We are to calculate the work done against the gravity. We are to calculate the work done against gravity. A shopkeeper lifts a tin of mass 2 kilogram vertical through a distance of 1.7 meters. Calculate the work done against gravity. Let's move to the solution. You can see there, this time we're supposed to work out for the force, but the distance has been given. We're supposed to be working out for the force. We know work done against gravity is given by the gravitational force, which is F times the distance. We know gravitational force is given by mg, as we are trying to take note actually in one of those previous slides. We noted that gravitational force is given by the mass of the body times the acceleration due to gravity. That's why we're having mg times h. In mg times h, we shall move to substitute. I did say that acceleration due to gravity is a constant, its value is 10. the mass of the body had to be in the SI unit. What is the SI unit of mass? What is the SI unit of mass?
Kilogram.
Kilograms.
Kilogram. So if the SI unit is kilograms, then we have to substitute there in kilograms. That's why you are seeing the 2. The 2 has not been changed because it is the SI unit, which is for mass, and it has remained in kilograms. And then G is acceleration due to gravity, which is 10. H is the distance, now the height through which this body, the body had to move. The shopkeeper had to lift the tin. The distance was 1.7 meters. So as we are calculating there, we shall have to substitute there. We have 2 times 10 times 1.7. When you press that well from your calculator, you'll be able to get it. I think 34. I know there are some of you who haven't calculators there. No, one of the gadgets that you should not miss to go with for mathematics, for physics lesson, is actually a calculator. When it comes to some calculations, you bring it just very close to yourself. So now they will have 2 times 10 times 1.7, get 34 joules. And then it gives for us the work done against the gravitational force. The last example, or the last question, I've tried to cut across areas so that we'll try to test your knowledge on so many areas as per the topic or per the concept. The engine force of 5,000 Newton pulls a train 100 meters from one station to the another. Are we together? Are we together, class? I suggest that when you're not yet contributing, you mute your microphone. You mute your Danish. Could you mute your I want Esther to read for us that question once again.
Engine of 5,000 newtons pulls a train 100 meters from one station to another. Calculate the work done.
In kilojoules.
In kilojoules.
Her voice, her audio is breaking. Gift, you always put in your microphone on. So let me give you this chance to say something. Read for us that question 3. Well, the question actually reads, the engine force of 5,000 Newton pulls a train 100 meters from one station to another. Calculate the work done in kilojoules. So now in this, see, there's nothing different from this. Only we are being tested, next slide, to now calculate the work done and the final answer be given in what? In kilojoules. Somewhere I gave in for you how you can be able to convert. You can see from the solution there, we are just calculating the work done, which is the normal way. It is force times distance. We just substitute as the force is in Newton. Then the distance is in meters. We just substituted so well there. But the answer we now got is 50,000 joule. 50,000 joule.
No.
Esther, you mute. Esther, mute that microphone. Bridget, your hand is up. Could you say something?
Answer, the answer is 500,000, not 50,000.
The answer
Yeah,
is
she's right, sir.
go ahead.
500,000, not 50,000.
So the answer is 500,000. Let me just get back there. The answer is 500,000. So let's, as we move on, that's correct. 5,000 times 100, you get 500,000 joule. Then we know, which has us have to work on few here. We know that now 1 kilojoule is an equivalent of 1 kilojoule is an equivalent of how many joules? 1 kilojoule is an equivalent of
1,000.
1,000. So which means we shall be dividing 500,000 by 1,000, and then we shall get what? 500 kilojoule. Is that okay?
Yes.
We shall be getting 500 kilojoules. That is how we can be able to calculate. So we shall be getting there 500. Then we divide by 1,000. Then eventually we ended up getting 500, which is kilojoules. The K is a small k. Small k. You know the difference between small k and capital J. So that would give us the answer there. So that is how we can be able to calculate work run. Basically today we have looked at work, the definition of work, the SI unit of work, and then the calculations. Okay. Now I want you people to have all this. Let's move to the next slide and we'll have this assignment. We have this assignment.
Teacher, how long is the lesson?
We have this assignment. This assignment is part of the lesson. It is to be done within the remaining time. These lessons are running for 1 hour. Is it okay? Our lessons here we plan and they run for 1 hour. This assignment that I've given, you'll be able to finish within the remaining minutes. Then you have your submissions. The submissions are going to be on the WhatsApp group there. Simply because many of you tend to, especially at night, have other discussions. And I think even here when we were for the lesson, someone was trying to say hi to another one. So it is always not so good for us to interact. Non-academic issues, we would not encourage them out of this. Maybe you can have that. You give a private chat or a private message for that kind of person, even if you meet a friend here. But why you meet here is for academics. So I would suggest that as we are going to interact in our WhatsApp group there, or even try to have our lessons here, let's pay attention to the ongoing lessons. So let's only keep it to academics. Dennis's hand is up. Dennis, can you? Dennis, Ruth, and Vera. I've given you the chance. Can you say out what you wanted to say? Because your hand is up. Dennis. Unfortunately, I think she cannot be able to hear from, though the hand is up. So that is the assignment that you're going to do. I hope you have taken note of, but it's still later on I'll be able to share that group. Is that okay?
I have my answer already.
You already have your answer. Then you can just post it to the group then. Thank you for listening and your active participation. I encourage us to always keep it to academics as we are here. Have a very good day. God bless you.
You have hands to respond.
Well,
Okay, bye. Yeah.
Thank
Patricia
you, sir.
and Gift.
Thanks. Yeah. Yeah.
Okay, welcome. Patricia and Gift, have you said something? Because your hands are up.
Thank you, sir.
You're welcome.
Thanks.
May God
I wish to get my I wish to get
Thank you, sir.
I wish to get my answer to the assignment in the group. Good day.
Yeah.
Thank you for the lesson.
Members, there is an
you.
announcement. Can
Bye.
you listen to it? Patricia, the floor is yours.
You're welcome.
Here. We are here listening.
Thank you so much. Mine is just a reminder of us.
We aren't getting you. You're breaking.
Hear me now.
We are not hearing you well.
We can't hear anything.
Find proper network. We can't hear you.
Okay, so about this. How about now? Now, can you hear me?
No, we can't. No, we can't.
Try speaking.
Somehow, you're not clear.
Try speaking, or else you will give us communication in the WhatsApp group.
Okay, move. Can you hear me now?